before the break we were at this point. So given this image, we said that if you convolve with the two of the kernels, that is what here. There is a kernel which helps in extracting the horizontal edges because it is vertical differentiation. There is the kernel that helps in extraction of the vertical edges. So accordingly, so this is the horizontal edge component.
Can we able to find out from that matrix only which one is horizontal or which one is vertical?
This is the matrix. What it is performing? It is performing. This is weighted average in the horizontal direction. This is weighted average in the horizontal direction. This is of negative polarity. This is of polarity. So after computing convolution with this, you get a single point, right? So in the image, the corresponding points were, this was 5, this was 7, these were the fixed points. In the horizontal direction, what it is computing, minus 5, minus 14, minus 3. Right? So that becomes minus 20. Because this is multiplied, this is multiplied, this is multiplied. Similarly for this, if the values were say 2, 9, plus something like this. So it is 2 plus 18, that is 20, plus 12. Then we'll go for vertical direction. This is minus 22, this is minus 32. Add them together, that becomes plus 10. Great. So plus 10 is the strength of the edge at this location. This is the center location. At the center location, this value that you are getting, that is the strength of the edge point, how strong the edge is. So that is the strength that you get at this point. Why I am saying that this will extract horizontal edges? Because I am doing differencing in the vertical direction. When I do differencing in the vertical direction, if there is discontinuity in the horizontal direction, there is vertical discontinuity, so edges have to be in the direction perpendicular. So this operator extract edge information which is in the horizontal direction. This one, in the same manner, this is doing differencing in the horizontal direction. So this will give you strength of the edge in the vertical direction. Right? So this is what you get to have. So this is the one which you get after convolution with this convolution. And this is the one that you get after convolving with the second convolution. So here you find that these are all horizontal edges. This one are vertical edges. If you combine these two, you get the compositions. Superimposition one for the other. So this is a kernel which tells you what are the edge properties of the areas that you have. Okay. Similarly, we talked about this Gaussian filter before. Right? This is what earlier we did is weighted average. Here that weighted average is basically the Gaussian filter, which is a short of filter. And then that is conferred with the cosine or sinusoid. That performs because sinusoidal one has got positive and negative poles. So that gives you differentiation. So it's a kernel which is integration as well as differentiation. That's a composite. And here what I can do is in this kernel, by varying the various values of theta, I can have a kernel in this direction. I can have a kernel which is in this direction. So all these things will be like this. By varying the value of theta, that gives you rotation. How frequent, what will be density of these sinusoidal waves, that is controlled by value of omega. Omega, that is the frequency. Right? So there we had some exponential, some term that involves x, y, sigma x, sigma y. Then we had that cosine omega x prime. We had this expression, right? This sigma x, sigma y tells you that how wide this convolution is, how frequent or how dense those cosine waves will be. That depends upon this value of omega. And what will be the orientation? That is this x prime direction of the kernel that is there. So whether it will be in this direction or in this direction or this direction, that depends upon the value of theta, which determines this extent. So I have three parameters here. One is sigma, that gives you a scale or spread over which you are computing this. How frequently or what is the frequency content in that particular region you have, that is determined by omega, and theta determines that in which orientation you are. So every combination of this sigma, omega, and theta, which is not explicit but implicit, because the direction of x prime is this direction of theta. So every combination of these three parameters gives you one kernel like this. One such kernel. So I can have multiple kernels. Okay. So when you conform and give an image given like this, each of the kernel will give you some sort of output like this. So if I have, say, 25 kernels for different values of sigma, omega, and theta, I have 25 such outputs for single image. If the images are different, maybe some of the outputs will be same, but at least there will be some outputs which will be different. And that is what will distinguish between the different images. Okay, so that is how you get this thing. And this is what you get is what is called as feature map. Every kernel gives you one feature map. Okay. These are again mathematical expressions of convolution in one dimension, convolution in two dimension. Without explaining this, let us see how this convolution is done. I'm doing it with respect to one dimension. Okay. So, suppose I have a convolution kernel which is like this. The center coefficient of the kernel is represented as WC. Okay. This is W minus 1, W minus 2. Somebody was telling that inversion. It is because of that inversion only, flipping. Right? Otherwise, W minus 1, minus 2 should have been on this side. So, first we have flipped it. Okay. Then you translate, shift at different location. At every shifted location, you get one value. Right? So this is how you are computing. Suppose my samples are this. One dimension. At 0th location, I have x0. Whatever be the value. This is x0 location. At that location, sample value is x0, x1, x2, x3, and so on. These are the convolution kernels. The way you perform convolution is after flipping operation, you get this, multiply this convolution coefficient with whatever is the signal value, this coefficient with the signal value, this coefficient with the signal value. You do all this, point-wise multiplication, add all of it together. That gives you one value at the central location, which is at the 0. Right? Next, what I have to do is shift this kernel. So W0 comes at the next position. Again, you do point by point multiplication of this. That gives you the next convolved output, which is Y1. Do the same operation, you get Y2. Do the same operation, you get Y3, and so on. So this is your convolution output. And the way we interpret the convolution is this convolution kernel is the response of the system to an unit impulse. Why unit impulse? Okay, if you want, I can explain that. The reason is, see, what we are doing is we are shifting and controlling with the unit impulse of the system, and that is what gives you what is the response of the system to the given input. Unit impulse, convolution operation is a linear operation, a bit of mathematics. A system is linear if it follows motility property and propagation. Okay. Any signal can be represented by shifted and weighted addition of impulses. Right? So this shifting and convolution, that takes care of impulse being shifted by some amount tau, right? That is what my signal at that location tau multiplied by whatever is the amplitude. Right? Add this for all those shifted and amplified impulses. That is why you convolve with impulse response of the system. If you do explanation in the frequency domain, the explanation is simpler, because if you take the Fourier transformation of the impulse, what do you get? It's a constant. Every frequency is present in an impulse, right? So given a system whose response at every frequency of the signal is given. Now in the frequency domain, this convolution is equivalent to multiplication. So you have a signal which has got a number of frequency components, impulse response given by the frequency domain multiplied by these two. Then you take the inverse Fourier transformation. Okay. So in case of frequency domain, the explanation is simple. So this is how the convolution is done in one dimension, right? How do you do convolution in two dimensions? I'll take a simple case. Suppose this is my 6 by 6 image. At every location, I'll have some values, right? Maybe 0, 1, 2, and if it is an 8-bit image, the values will vary from 0 to 255. So this is an array of integer numbers. Let us assume that number can be anything from 0 to 255. This is my convolution kernel. So I'll have different convolution coefficients or kernel coefficients, right? First, what you do? As before, the kernel has to be flipped both horizontally and vertically because this is a convolution operation. Put the kernel at this location. Do point by point multiplication. Add all of them. So this sum that you get, that is your convolution output at this location, the center of the kernel. Next, you shift the kernel. This is what is called stride. When you talk about deep learning, this process of shifting is called stride. So you can shift by one, you can shift by two locations and all that. Whether you decide stride to be 1 or 2. That will decide what will be your output of the convolved size. Okay. You perform the same thing at the shifted location, you get the second value. You continue like this, third value, fourth value, and so on. So compute over all the image locations. Finally, I get the output. So this will also be some numerical value, right? And this numerical value tells that what is the response of the input image to a system having this impulse response. So this convolution is nothing but a response, right? So if I have different images or different input signals, as long as kernel is fixed, my system is fixed. So what is the response of the input signal to this particular system? That is what is the convolution, right? So obviously if I have different signals, my response will be different. And with that, help of that, I can differentiate between different signals. So as I said, stride 1, I get this size. Stride 2 means I shift the kernel by 2 and perform the multiplication addition operation. And obviously my convolved output size will be this. Okay. So a CNN architecture, convolution neural network architecture is something like this. You'll have first a convolution layer. So I'll have a number of such convolution kernels with which the image is to be convolved. I get the convolution output. Then the nonlinearity, we said in case of neural network, I have different types of nonlinearity. I can have threshold nonlinearity, sigmoidal function and all that. Over here, the nonlinearity which is used is what is called a value. The reason is, in case of deep neural network, I mean, why is it deep? Why the name deep has come? You find that the strength of the network in terms of modeling a nonlinear function depends upon how many layers you have. Right? In case of deep neural network, the number of layers is quite high. In normal network, maybe maximum 4 or 5 nodes, which are called shallow networks. In case of deep network, the number of layers can be 100, maybe 1,000. Okay. So with this type of networks, you think of that we talked about this sigmoidal function, but the function response output of the neural node is like this. And learning that you are doing is by using the differentiation function. So if my output response is somewhere over here, and I differentiate this with respect to parameters, the differentiation is almost 0. Because here the output is almost constant. The differentiation output is almost 0. So as a result, my parameters will not be modified because my gradient is 0. So that is the problem with this kind of activation function. Instead, if my activation function is linear, then everywhere the differentiation is constant. Right? So this is the purpose, this is the reason. And of course, this difficulty becomes more and more severe as you increase the number of layers. So this is the reason that in case of deep neural network, you don't use the sigmoidal function, or even a similar such function is canonical hyperbolic function. You don't use that, but you use a partly linear, partly non-linear, because in case of value, the negative side is done. So this is the kind of activation function that is used in case of deep neural network. So here I have the convolution operation, followed by convolution, I have nonlinearity. Followed by nonlinearity, there is another layer which is called a pooling layer. I can have different types of pooling, like max pooling, average pooling, and all that. The purpose of pooling is to reduce the dimension of the feature map that you generate. And at the same time, in case of pooling, what you do is, suppose you do pooling over a 4x4 window, or let us take a smaller one, say 2x2 window, and the pooling is max pooling. So I have a 2x2 array. Out of that, next layer, what I feed after pooling is maximum of these 4 activation values. So suppose my values are 4, 10, 3, 9. Maximum is 10. 10 will be fed to the output and will go to the next layer. So this pooling has, one is reduction of dimension, because out of 4 I am selecting 1.
So will be a translation in value?
Exactly. It will also be to some extent translation. Because if I shift the window, that 10, it is likely to be 10 in the next neighborhood also. So even if my signal is slightly translated, I get my next neighborhood. So to some extent, it is translation. And the other advantage is, when you perform convolution, you find that the convolution output is local, right? I'm doing convolution over a window of 3x3. So whatever response I get at that location, it is the response from that 3x3 window only, not outside that. So the response that you get is the local response. When I go for pooling, I'm selecting one out of many responses in a particular neighborhood. So I also do a transformation of local to global transformation, because I'm selecting a feature over a larger group size. So those are the three advantages of having pooling. And when you have a deep neural network or convolution neural network, we can assume that this is a unit of a stack of layers that it has. So I'll have one unit of convolution non-linearity pooling, another unit of convolution non-linearity pooling, another unit of convolution non-linearity pooling. I'll have a cascade of such layers. Finally, this is what is the neural network that we discussed earlier. Right? So up to this, through convolution and nonlinear operations, you are extracting the features. So this is the feature vector that you said in the earlier case to the input of the neural network. This part is the multi-layer neural network, which is fed to the multi-layer neural network, and this multi-layer neural network gives you the output of the classification that given an input image to which class that image belongs, or whether this image is the image of a dog, it's the image of a bird, image of a mango, whatever. Okay. And the entire training will be same, following the back propagation and gradient. Right. How many features you select, that depends upon how many convolution kernels I have. If I use 2 convolution kernels, I have 2 feature groups. Every convolution kernel gives 1 feature. If I use 10 convolution kernels, I'll get 10 feature groups. Okay, like the different features that we extract. Is that okay?
So in multi-layers are the hidden layers.
Truly speaking, except the first layer and the last layer, all should be called hidden layers. But in case of deep neural network, we don't talk about hidden layers. In case of this multi-layer perceptron, we talk about hidden layers. In deep neural network or CNN, we don't really talk about hidden layers because these layers are not taking any decision in classification. These layers are giving the output of feature extraction. So they are helping you. Right. So they are not really classification networks. Whereas this is the one which is classification. This is the same as the earlier networks that you said, that you feed the feature vectors to the network, and the network gives you the classification, that to which class that this feature vector belongs. That is what is this. These are the ones which are replacing our feature extraction part. Initially, you said hand crafted feature vectors. Then we talked about autoencoder. So whatever is the job of whether it is handcrafted feature vector extraction or autoencoder, that job now is being done by these layers. Okay. And every layer, you are getting some feature at certain resolution. Here, I have the highest resolution. Then through pooling, I am reducing the dimension. Say if it is max pooling over a window size of 4x4 or 3x3, whatever I select, out of 2x2 or 4, I'll select in one. That means you are reducing the resolution. So at this level, I get features at the highest resolution. As I move towards the end of the network, I get features at lower resolutions. Okay. Depending upon how you use these features, whether I use features only at the last layer for classification, or I use combinations of the features at different layers for classification purposes. I have different architectures of data. Great. So let us see. Some of the popular deep neural networks. is, animation is not working on this. This was an animation showing that how this window actually shifts for computing of features at different points. Okay. So that animation is not working. I was taking multiple kernels. So this one is one kernel, this is another. Doing convolution on the same image. So this red kernel gives you one feature, green kernel gives you another feature. So I get two sets of features. These are called feature maps. How many such feature maps we have depends upon how many kernels we use. Okay. Earlier I talked about Chauvel's kernel for its detection operation, -1, -2, -1, which are fixed kernels. Similarly, Gabor kernels are fixed kernels. In this case, the kernels are not fixed. Initially, you choose a kernel at random, or the coefficients are chosen at random. Then those are fine-tuned. Earlier I said that you fine-tune the weights. Here, in deep neural network, you fine-tune the kernels also by backpropagation algorithm. Because output response is nothing but a function of kernel coefficient values. Okay. So in the same backpropagation manner, in the same gradient descent procedure, I can also fine-tune the kernel coefficient values. Okay. So that is how you get all these different features. So this is again the same thing. This is the non-linearity that I said. This is pooling. I have already explained this. So this is what I said. Suppose I do max pooling over a window size of 2 by 2. So over here the maximum value is 9. 9 is chosen. Over here maximum value is 6. 6 is chosen. Over here maximum value is 4. 4 is chosen. From here 8 is chosen. Right? So this is what the max pooling operation does. And these are the values which will be fed to the next place. Okay. So one option is I choose only these values for final classification, or I can combine this and this for final classification. And that decides what is the architecture of the deep neural network that we use. There is a process called normalization. I think I'll just introduce why normalization is required without going into mathematical details. Yeah. When you train such a neural network, the neural network is usually trained in batches. Right? I have to give some positive class, some negative class. Say for example, I'm training the neural network so that it is able to detect or recognize, say, lotus. So I'll have a number of samples which belong to lotus, which are positive class. I also have to have a number of samples which are not lotus. That may be anything, which are negative class. So suppose this is an example that I want to train a neural network which is to detect flowers against non-flowers. And this training is done in batches, right? In every batch, you give small positive class samples, small negative class samples. So this is one batch of data. These are the positive class samples. These are the negative class samples. There is another batch of data. These are the positive class samples. These are the negative class samples. Now you find that there is a characteristic difference of the samples that you have taken in the batches. In this batch, these flowers are not very colorful, whereas these flowers are colorful. So when you train the network, in this batch, I'll get some classifier. But the same classifier, when training with the other batch, we can use some other classifier. But my purpose is. So what you get is something like this. Suppose these are the feature vectors for these positive classes. These are the feature vectors. All the signals are different. The distribution of the feature vectors will also be different. So suppose the distribution has changed in very small. And when you train with this, your boundary within the classes is this one. So you find that there are two different situations. I want to tell one classifier to classify flowers from non-classifier and non-flowers. This set of examples gives me this classifier. This set of examples gives me this boundary. So now my classifier is confused. So for different batches, you will find that the classifier hops from one boundary to another. As well as, so because of this, your training process will never converge. It will be very, very slow. Not only that, ultimately you may not get any output at all. Your classifier may not be well trained at all. So this is what is known as covariant shift. So to avoid this covariant shift, we have to normalize the signals. We also have to normalize the activations at different layers. And that is what is known normalization process. Okay. So there are mathematical techniques for normalization. I'm not going to mathematics. So different types of normalization operations that we can do is, we can go for batch normalization, we can go for layer normalization. The only purpose is that you represent your feature vectors or the activation functions of the input signal in the same frame of reference. In earlier case, the frames of references are different in different batches. Okay. So this is the purpose in which we go for this normalization. I'm not going into details of this. The different normalization operations, that normalization, instance normalization, normalization. The difference between multi-layer perceptor and CNN. The basic difference is in case of CNN, the weights are actually shared. Because for a convolution kernel, it is the same convolution kernel which is working over the integers. Right? Whereas, if I want to do the same thing using multi-layer perceptron, then for every pixel, I have to have a weight. So the number of parameters that we get in an equivalent multi-layer perceptron, equivalent to CNN, that will be much more. You can reduce the number of parameters which help in the process. So these are some popular CNN architectures. I will particularly go to a CNN architecture which is very, very popular is BGG. Okay. So again, you find that at different layers, you have kernels of different sizes. Okay. And from there to there, yeah. So that pooling operation, you are reducing the kernel size, the feature size. Because that is done. Another popular network is GoogleNet. Also, you all have heard about it. You'll find that in GoogleNet, expansion itself will take more than 1 hour. So let me not try that even. You find that there are convolution kernels of different sizes. Okay. I have convolution kernel of 3 by 3, you have convolution kernel of 5 by 5, and all that. So you have convolution kernels of different sizes. When you have convolution kernel of different size, of a larger size, that means you are extracting feature, computing feature over a larger size. Okay. So you get, in the same layer, you get features of multiple resolutions. And you take action based on all those multiple resolution features. It has certain important features. One of the features is these are called auxiliary networks. You find that as the depth of the network is very high, when you go for backpropagation, if you want to backpropagate this final error or derivative of the final error to the input layer for modification, the network may not converge. So there are intermediate classifiers which are called auxiliary classifiers. You combine this final error with the auxiliary classifiers for that input. That is what that suggested. And this is VGG and GoogleNet. They are the most successful deep neural networks are they were tested against what is called image net contest, right? For classification of different images of different categories. I think let me stop first part over here. So now I hope you have, I'll not say you have become expert. Even today I'm not an expert. Okay, I'm still learning. But you have a rough idea of how the neural network, how the deep neural network or CNN network that works. Right? So with that, I will move to my how do I come to the next set of slides? Home. See how I have learned? So error only, right? Do the mistake, rectify the mistake. So now let us see what is generative. But before that, let us see what we have done till now. See, so far what we have done is, we have taken images from different classes. Every such class has a distribution. So if I call it class X, it has a distribution. So you are taking a sample from a distribution Px, giving it to your classifier. What the classifier estimates is what is the probability of Py given X. Y is the class. That is my posterior. Okay. And for whichever the posterior probability is maximum, you are classifying your input sample X to that particular class. Right. Now the situation is, if the output of this network matches with your ground truth, which is Y, when I'm pretending, I'm also feeling that this X belongs to this Y. If this matches, then I don't have any error. So I don't need any retraining or modification of the parameters, right? But if it does not match, then what I have is an error or a loss, and through backpropagation for the gradient descent procedure, you minimize this loss or minimize this error. That is how you modify the parameters. So here what we are doing is, you are trying to discriminate among different distributions. For different X and different distribution, we are discriminating cat against dog, we are discriminating cat against bird and all that, right? So this is a network which is called a discriminative model or the discriminative model. How you are discriminating? Final discrimination event in our deep neural network is the final few layers which are multi-layer perception. That is what discriminates. Before that, CNN, non-linearity, spooling, it does not discriminate. It tells you the features. These features are used by the final layers for discrimination. Okay, and that is what the MLP learns, that is, it learns given an x, what is pyx. That is what it learns. Right? In a disconnected. So, in a generative model, this is just a statement by Richard Feynman, the great physicist, right? That what I cannot create, I do not understand. That means, if I am able to say that this is a cat, even if I am not a good artist, but I should be able to make a sketch of the cat. It may not look good, but I should be able to make a sketch. Okay. So if I am unable to do that, then it is properly understood that I did not understand what it is. So for this, what you have to do is you have to collect a large set of data from different domains, and you have to train a network or a model so that after learning from this data, the model should be able to recreate that. That is what is called generative. Right? Suppose, now let me come to my feature vectors. What we said earlier, right? My classification is based on the feature vectors. What does feature vector take? It gives you different attributes or different properties of the same. Okay. So suppose my attributes are like this. One of the attributes is whether the animal is big or small. It is suppose for an animal. The attribute says that it is a big animal. The animal has 4 legs. It has big ears. It has long trunk. It has pair of tusks. These are the attributes which are given. Can you guess what this animal is? Exactly. So perfect generator. It's an input, right? So we want a model that if we give this sort of descriptions to the model should be able to generate this. That yes, it is an it's a good and it should be a problem. These are what are called latent variables. Earlier we said features, feature vectors. The moment you move from machine learning to deep learning, it is just change of term, nothing else. Now the features are called latent variables. The feature vector is called latent vector. That is the only difference. Okay. So that brings it to our old concept. We talked about autoencoder, right? In autoencoder, you feed an input signal. I have a bottleneck layer, somewhere in between. The bottleneck layer gives you, now let us call it latent vector, it is nothing but a feature vector. And the decoder part takes that feature vector, decrypts the image. Right. So this is nothing but a generator, which is taking the description, and from that description, it is generated. It is a sort of generator, that is true. I will not deny. But this generator is not sufficient. This generator has been trained only on those feature vectors which this generator has seen. Right. So you have given an input signal. At the middle layer, you have the feature vector. This feature vector the generator has generated to the signal again, and I have been able to generate it faithfully because I had the loss function between the input and output, which was minimized. Right? But the feature space that is generated by this encoder, it's a sparse feature space. It is not dense or it is not continuous. When I come to the generator, true generator, I should be able to sample any arbitrary feature vector from that learned feature space, give it to the generator should be able to generate an image belonging to the same domain, even if the network has not seen that image before. That is the purpose of this generator. But here, the generator or the decoder or the autoencoder will not be able to do it, because that was not my purpose. My purpose was the encoder part gives you a feature vector which is sufficient for classification. And how we are classifying? It is nothing but based on a distance So even if the feature vector that I generate is not exactly same as one of the before, but if it is similar to the before, I can classify it. So classification was there, generation was there. Okay. So what I want is, suppose I have two different domains. Say one domain is a domain of Barbie dolls, another domain is a domain of fish. Right? When you train your autoencoder model, the autoencoder model has generated one feature space for Barbie dolls, another feature space for the fish. Though even if I sample a vector from the Barbie doll features, give it to the generator cannot be able to generate one of the vectors. In addition to that, I also want that if I sample a vector from somewhere in between the distribution of the feature vectors of the Barbie doll and the distribution feature vectors of the fish, my generator should be able to interpolate the properties of these two to give me something which is realistic. Right? So here, if I sample a feature vector, this is where I have the region of all the feature vectors belonging to Barbie doll. Here I have a region which is the distribution of all the feature vectors of fish. If I sample a feature vector from here and give it to the generator, what the generator will generate? It should be a mix of these two, right? I should be able to interpolate. So this is what I expect. But autoencoder will not be able to do that. Okay. So when I talk about generating model, the generating model should be able to do this. And for doing that, what I need is the feature space should be continuous. It should be length of continuous. And the feature spaces of different domains should be close enough so that interpolation is possible. If they are wide apart, this fellow does not know what it is, this fellow does not know what is this, then the interpolation is not possible. So that is the aim of the generator. So we'll have a variant of something like autoencoder, but with an additional provision that that particular autoencoder should be able to estimate a continuous distribution of feature vectors, or should be able to model a continuous feature space. Okay. So again, there are a lot of mathematics, and I also want that these two different distributions should be very close. Okay. Now, the distribution for a particular class is possible using the reconstruction laws. That is, when we say x and x hat, the similarity between these two, if I want to reduce the dissimilarity between these two, I get feature space of a particular class. In addition to this, for interpolation, I also want that different feature spaces should be very close. So that I can do if I impose a condition that all these different distributions should be close to a single distribution. That is the distance of the, when it is this distribution, I will not call it distance, but it is the divergence. Because if I say distance, if there is anybody from mathematics, you know that the moment I say distance, it has to follow certain specific properties. Right? So I will not call it distance, it is divergence. So if I give a target distribution, and I want that all other distribution of the feature vectors belonging to different classes should be similar to this. So in that case, I have to minimize the divergence of this feature distribution and my target distribution. So now I have two loss components. One of the component is the reconstruction loss, that is the error between x and x hat, and other one is divergence loss, which is the divergence between my target distribution and the feature, class dependent feature distribution. You minimize these two losses to tame your network. Right? So I have some examples. So by this distribution, what I mean is this. You find that we have these three different images, right? And if one of my attribute is mine, this is one of the attributes, right? in case of this, all of you know this image, right? Mona Lisa. The famous Mona Lisa in, right now it is in Louvre Museum in France. Right? It's a neutral face. She is neither sorrow nor happy, neither sad nor happy. Right? It's a neutral face. So smile, following our autoencoder, the attribute smile will help them. Because it is neutral. Come to this lad, very sad. So the smile will have negative. This fellow smiling a lot, so smiling will have positive. And these are the attribute values which will be computed by the autoencoder that is said. When I want a generative model, that kind of crisp vector is not enough for me, because I don't know what to create for a value somewhere over here. Right? So I want, instead of that crisp value, there should be a distribution. It should have a mean value, because this space is sad, the mean value will be negative, but there will be a variation amount. Okay, so that my generator knows that even if I have a sample over here, it's a degree of sadness or degree of happiness. Accordingly, the generator should be able to generate this. Similarly, over here, it is neutral, but there is a degree associated. Here it is happy, but there is a degree associated. So that is what I mean by a continuous distribution. This is what is discrete. Right? So again, I will not go through all the mathematical details. These are, yes. So my generator model should be the concept. This is my input signal, X. This is the latent vector or the feature vector Z. Right? What the encoder part does is, from X, it generates Z. That is what is your encoder. Right? Because in encoder, we had two layers. Here you are feeding your input X, here you are getting X hat, here I had the input layer, which gives me the feature vector. In case of autoencoder, we said that we just demonstrated this X is a crisp vector. Definitely helps. I want this should give you a distribution of features. Okay? So my model is something like this. If you have X, to find out Q of Z given X, what is the probability you get a feature vector Z for a given input X. Reverse process is my generative process. Given an input vector Z, sampled from the feature space, I should be able to generate an X belonging to the set. Okay? So my model is similar to autoencoder model, with a difference that now this bottleneck layer will not give me a feature vector, but it will estimate distribution features. Okay? And this distribution, typically we assume it is Gaussian distribution. Okay? So it has to estimate what is the mean of the distribution and what is the variance or standard deviation of the distribution for different data's. That is what is expected. Right. So this is this one. This is the encoder model. Now it is not called autoencoder, but this is called variation of autoencoder. the variational comes from a mathematical term, which is variational. I did not go into it. Okay. So that is the one from where the variational encoder comes into picture. In case of variational autoencoder, what you try to learn is the mean and variance of the frequencies. Okay. And a sample from this distribution is given to the encoder part of the generator part, and the generator should be able to generate an image belonging to that particular domain over which the network is. So it is a distribution of domains. Now, again, I am not going to this, I'm not going to the details of this one. Let us see what is such a network can do. Okay. These are the images which are generated by a variational autoencoder after training over semi-pretty database, face images. Right? So you find that the images are quite photorealistic. Okay. This is where in the morning I said the risk of generating. Right? If you can generate so photorealistic images, you can generate photorealistic video. You can also generate audio by another network. You can superimpose that audio on that video to impersonate somebody. So even you will not be surprised, possibly, if tomorrow on the network you find that Professor P.K. Biswas is giving lecture on this. Quite possible using this generator. So such a type of impersonification is possible using generator. So that is why I said that now things are coming up to response through AI. The artificial intelligence has to be responsible, and I said to make it responsible, people who are generating it, designing it, people who are using it, all of them. So this is what is variational autoencoder. There are some mathematics on top of variational autoencoder. The vector algebra is also happening. So something like this. You can train a model with faces without specs. You can train a model with faces with specs. Take the difference of these two, you can generate on this space.
The deep fact is kind of.
Exactly. It is this one. So it has got of this. So one is very important. The other kind of generative model is what is generative adversarial. The philosophy is slightly different from what we have done in prediction. In generative adversarial network, it is something like this, that I have a generator model, I have a discriminator model. That discriminator acts as a critic in the sense that the generator generates something, okay? And the discriminator says whether what has been generated is real or fake. Right? So the generator will always try to generate something which looks real. Discriminator tries to say that what the generator has generated is not the real one, but it's a fake one. The generator takes that feedback from the discriminator, because if it is fake, obviously the generator does not want it. So that is an error which is coming to the generator. So using this feedback, the generator